is a principal researcher at ByteDance and serves as the managing director of the supply chain area team. Zhou has a very expressive track record in forecasting and supply chain and traffic flow. He's dedicated to harnessing the power and machine learning to solve real-world industry problems, promoting the application of advanced technologies such as deep learning, statistical learning, and operational optimization. Okay. So the second speaker is Shiyu Wang. He is a senior staff researcher at ByteDance and serves as the director of the supply chain algorithm team. His current research primarily focuses on the time series tasks based on deep learning and the development of larger models for time series. So to first off, let's invite Shiyu, right? This is a joint presentation, okay? Okay, thank you.
Hi everyone, I'm Shiyu Wang from ByteDance. I'm excited to share with you the large time series models, industrial frontier research, and global supply chain applications. The success of modern e-commerce heavily relies on the management of global supply chains. From the moment a customer places an order to warehouse preparation and finally to fulfillment center delivery, every step requires forecasting and planning. From demand forecasting to procurement planning, inventory stocking, warehouse manpower allocation, and logistic delivery at the fulfillment center. Time series forecasting is everywhere in every part of this whole process. Therefore, one of the key factors for successful modern supply chain management is the advancement of time series forecasting models. Let us uncover the progress of time series forecasting in supply chain. Let us now take a look back at the development history of time series model. This timeline illustrates the evolution of time series modeling, starting from traditional statistic methods like hot winter and RIMA, to modern deep forecasting model and billion scale large time series models. Significant advancements include the introduction of deep learning-based models such as TCN and MBITS, and DeepAR, followed by transformer-based architecture like informal, outformal, and NS-formal. Recent breakthroughs such as time mixture, I-transformer, time RRM, and time MOE represent a new era of high-dimensional forecasting and general time series pattern modeling. These developments highlight the rapid progress in handling complex and large-scale time series data. Following the historical advancement of time series models in recent years, we will introduce it in 4 parts. Part 1, multi-scale time series analysis. Considering the ubiquitous multi-scale characteristics of time series, especially in the complex e-commerce supply chain field, we will introduce time mixture and time detail, which represent multi-scale time series modeling and multi-scale time series distillation. Part 2, high-dimensional time series forecasting. In supply chain of e-commerce, SKU typically number in the tens of thousands, and the sales sequence of SKU form a high-dimensional time series. Therefore, in part 2, we will explore the advancement in high-dimensional time series forecasting, introducing I-transformer and its upgraded version, UCAST. Part 3, multimodal time series analysis. Breaking the boundaries of time series, we move towards multimodality. In the e-commerce domain, text-true data far exceeds time series data itself, especially considering the recent groundbreaking advancement in large language models. In part 3, we will introduce how to leverage reprogramming to active the capabilities of large language models, enabling multimodal time series analysis. Part 4, towards large time series models in supply chain. Scaling law have now become the golden rule in the field of deep learning. Following the successful path of large language models, we move towards large time series models. In part 4, we will introduce the general time series pattern machine and the billion scale large time series models, along with their application in supply chain management. In the first part, it is necessary to discuss the characteristics of time series. In the figure, we observe patterns like uptrends, downtrends, plateaus, steep draws, and fast actions. These patterns pose significant challenges for analysis and forecasting for time series. So we have a question: how to tackle intricate temporal variations? To address this, we propose two key approaches. First, decomposition. Second, multiperiodicity. Both approaches point to one key concept: multi-scale analysis. Time series data has multi-scale properties. For example, traffic change daily and weekly, while weather change daily and yearly. We analyze this use different scales. Core scales shows global and big trends, while fine scales shows local and small details. This helps us understand both microscopic and microscopic information. So, how to utilize these disentangled multi-scale variations for time series forecasting? This is a key point to success. In light of this, we have two observations. Observation 1 is about history extraction. Signal and trend paths have different mixing properties. Fine scale signal and coarse scale trend are very important for time series forecasting. The left figure shows mixing weight for signal and trends, and the right shows predictions for different scales. This helps us understand and predict time series better. Observation 2 is about future prediction. Future trends depend on multi-scale past data. Different scales work together to improve forecasting. This figure shows predictions at 4 scales. This also helps us understand and predict better. We can intuitively see that predictions at different scales capture different aspects. Core scale focuses on trends and global future, while fine scales focus on seeing and detailed patterns. Building on this, we present a novel model called time mixture. This is the overall design of time mixture. First, in part A, we title the input series and create multi-scale time series using downsampling. Next, in part B, we use partial decomposable mixing to extract history information. This includes decomposition, signal mixing with a bottom-up method, and trend mixing with a top-down method. Finally, in part C, we use future multi-prediction mixing to make predictions by combining multiple predictors. This is the detailed design of partial decomposable mixing. First, we compose the input series into signal and trend components. Signal mixing uses a bottom-up method, while trend mixing use a top-down method. These components are combined using feed-forward layers to extract history features for future prediction. This figure presents the future multi-predictor. It uses multi-predictor to handle multi-scale time series. Each predictor falls on a specific scale and make predictions. The final prediction is the aggregation of all predictor outputs. This approach helps us capture patterns at different scales for better accuracy. Our experiment includes long-term forecasting and short-term forecasting with datasets like ETT, weather, solar energy, electricity, and traffic patterns and M4. The benchmarks use 15 baselines and 2 experiment settings, unified and searched hyperparameters. TimeMix achieves state-of-the-art performance in all benchmarks and all settings. From this table, we can observe that TimeMix performance very well across all datasets, demonstrating state-of-the-art performance whether using unified setting or searched parameters. Compared to other models in this showcase, we can clearly find that TimeMix itself captures both season and trends. To demonstrate the advancement of TimeMix, we plot the spectrogram of ground truth and model predictions. It's observed that TimeMix captures different frequency paths precisely. This slide shows the short-term forecasting results from multivariate data using TIMES dataset. The input is 19.6 time steps, and the model predicts the next 12 steps for 5-minute traffic data. The number of variables ranges from 100 to 800. This table compares the performance of TimeMix with other models based on 3 metrics: MAE, MAP, and RMSE. TimeMix has the best result in most cases. This shows that TimeMix is very good at spectral-temporal correlation modeling and works very well for traffic data forecasting. This slide shows the short-term forecasting results for unified data using the M4 dataset. The prediction range from 6 to 48 steps and include diversity temporal variance from hourly to yearly data. The table compares the performance of TimeMix with other models for each frequency. We can see the evolution matrix SMAP, MASE, and OWA. TimeMix achieves the best result in most cases, especially for yearly, quarterly, and monthly data. For example, in the yearly category, TimeMix has the lowest SMAP, which is better than all other models overall. TimeMix demonstrates excellent performance across all temporal variations, achieving the best weight average results. This highlights its strong capability in handling diverse forecasting tasks. This is an application study for TimeMix. We test different designs to see how they affect performance. The table shows results for 3 datasets M4, PAM04, and ETT M1. The first row is our full model, which performs the best. For M4, it has the lowest SMAP, MASE, and OWA. For PAM04, it has the lowest MAE, MAP, and RMSE. For ETT M1, it has the best MIC and MAE. Other rows show models with some feature removed. Removing features makes the performance worse. This shows every design in TimeMix is important and effective. This is the efficiency comparison for TimeMix and other models. The left chart shows GPU memory usage for different series lengths. TimeMix use less memory than most transformer-based models like autoformer and FedFormer. The right chart shows running time for different series lengths. Time makes to run faster than many transformer-based models, especially for long-term series. This proves time mixture is efficient in both memory and running time. Following the path of multi-scale analysis, we will discuss how to apply the concept to knowledge distillation for time series. In this section, we will explore the knowledge distillation for time series with multi-scale method. Distillation is motivated by the need to balance efficiency and performance. Using a teach-student framework, knowledge is transformed from a large complex model to a small, simple one. This allows us to achieve strong performance with low computational costs. Different models excel on different subsets of data, as shown in the table. By leveraging distillation, we can combine the strengths of these models, improving overall results while maintaining efficiency. This process is key to optimize performance in diverse scenarios. In general, we focus on two aspects to distillation: multi-scale pattern and multi-parent patterns. On the left, we can see how different models perform across various scales of the electricity dataset. The MIP model struggles significantly, especially at smaller scales, while other models like PatchTST and Transformer capture the patterns much better. This highlights the importance of understanding multi-scale behavior in terms of data. On the right, we compare the prediction spectrograms of different models to the ground truth. The MIP fails to match the amplitude of key frequencies, which noticeable different markets in the right. Other models, however, perform closer to the ground truth, showcase their ability to capture multi-parent patterns effectively. This demonstrates why these two aspects are critical for improving time series knowledge distillation. So, in light of this, we introduce our methodology named time distill, combines two key distillation strategies: multi-scale and multi-parent distillation. On the left, we see the multi-scale distillation process. The input time series is done simply into different scales, capturing patterns at various levels. The teacher model predicts at each scale, and the student MIP learns to match these predictions. Ensure it captures the multi-scale structure of the data. On the right, we have multi-parent distillation. Here, we use FFT to extract the frequency components and compare the spectrograms and predict distribution between the teacher and student. This ensures the student learns key predicted patterns. The overall framework integrates this idea at both the future and the prediction levels with the total loss combining supervised loss, scale level loss, and parent level loss weighted by alpha and beta. This approach helps the student model learn both scale and the parent information effectively. So we can observe that time distill outperform the baseline on 7 out of 8 datasets on MSE and all datasets on MAE. To further, we compare efficiency and performance across different models. What we see is that many state-of-the-art methods like transformer-based and CNN-based models have poor efficiency. For example, modern TCN has high accuracy, but a very large parameter size and a slow inference time, making it unsuitable for real-time applications. On the other hand, models like time-distance and MIP are much faster and lightweight, but may sacrifice some accuracy. This trade-off is critical for latency-sensitive tasks such as financial prediction and healthcare monitoring, where fast and efficient inference is essential. Balance speed, accuracy, and model size remains a key challenge in these applications. I will now pass the next part to my partner Zhou Ye. You can also call Vincent. He will guide you through the gateway to exploring the high-dimensional time series.